when studying three-dimensional vectors, you're going to be running into extending what you've learned in 2 dimensions to 3 dimensions with regards to adding vectors together, subtracting them, which is really just the addition of 2 vectors, and one of them is the opposite vector, taking it with scalar multiplication, and then extending the 2-dimensional dot product to 3-dimensional dot product. Now, what's really nice is when you get into 3 dimensions, actually nothing really changes much in terms of adding, subtracting, scalar multiplication, and even the dot product. So when you're coming across through these, I'll try to explain these just through simple examples. Now, I am assuming that you are familiar with the notation, so the Cartesian vector notation for vectors in 3 dimensions, and I can put up a link up above there to the introductory video, okay, which talks about that. Now, I'll take a look first at adding the 2 vectors, or possibly subtracting 2 vectors. So you may recall, so if I give you an example here, for instance, if we had vectors that were in 2 dimensions, so you just had the x and the y components, and let's say here's the other vector, so maybe -3 and 4. If you wanted to be able to add these together, well, all we had to do was add the actual components of each, and so we would just say 1 plus -3, which would have been -2, and then 2 plus the 4, which would have been 6, and we would have obtained our resultant vector. So it was really nice and easy to add vectors in Cartesian vector form because it's just what we're very much used to doing in terms of addition of just simple numbers. Now, if you are going to extend this to 3 dimensions, well, it turns out that there is really no difference. So if I would give you 2 vectors that you would have, so let's put 1, 2, but now I'm going to add a component which is going to have the 3rd dimension. So this is a vector in 3 dimensions now, and you're going to be adding it to another vector. So let's say 3, 4, and maybe this was -2. Well, in this case, you once again are going to just simply take each component. So these 2 we've already done, so we know that that is -2 and 6 right there. And then your next component, which is on the z-axis, so this is the 3rd dimension, you would do exactly the same thing. So it would be just 1 plus -2, which would have been just -1. And when students see this, it's a little bit of a joy because you can extend 2 dimensions to 3 dimensions rather easily. To be honest with you, you could have extended this to the nth dimension. It could have been the 4th dimension, 5th dimension. Now, we wouldn't be able to really visualize those much, but you would actually be doing exactly the same thing with the vectors. So once you learn 2 dimensions and 3 dimensions, the extension is rather simple. The complication becomes of trying to visualize it and getting intuition into the actual further dimensions than 3. But the math is pretty straightforward. Now, if you are going to be doing subtracting, well, in subtraction, you do exactly the same thing. So if I take the 2 vectors, so as I have them right here, so I'm going to just duplicate this. I'm going to bring it back down. Now, instead of actually trying to add these together, if I'm going to try to subtract the 2 vectors together, again, you can just take each component one by one and then break it down. So 1 minus -3, which now is going to be 4. 2 minus the 4, which is going to be -2. And then finally 1 minus the -2, which is going to be 3. And here is your resultant vector. So here is subtraction following with the same process as addition. And this isn't anything spectacular at all, right? So this is exactly what you are doing in 2 dimensions. So it's nice to see that 2 dimensions do indeed extend into 3 dimensions without any kind of a hiccup. Now, what happens if you have scalar multiplication? Now, so you may recall, so if you have a scalar multiplication, so the actual property, okay, so within here becomes that if you take a scalar, so this is some scalar, so some element of the real numbers, and you're trying to multiply it by a vector, I'm going to just assume that the vector itself, it is three-dimensional, so it has the x component, it has the y component, and it has the z component right there. Well, if you're going to be trying to do this scalar multiplication, it is nothing else but simply distribution right across. So if I gave you an example and I took the resultant vector, so let's say maybe I took this one from the subtraction, I'm going to duplicate it and bring it down in here, and I had some particular scalar to be able to multiply this with, I don't know, so let's say maybe 3 right in here, and you wanted to find out what the resultant vector is, you may recall from 2 dimensions, then this just simply would mean you're scaling the vector, right, by 3. So now I'm not going to draw this particular vector at all, okay, within here, but let's say that the vector, okay, this was my v right there, and if I would multiply it by 3, all I'm saying is I'm taking this vector and then I'm making it bigger by 3, okay, so I can literally line them up, so there we go, it would have been 3 times bigger, and that is my resultant vector. Now, to find the actual values, well, you can just bring this right inside and you can find your result. So 3 times 4 is going to be 12. So it's 3 times bigger for the x component. It's going to be 3 times -2, which is -6. So again, 3 times bigger for the y component. And 3 times 3, which is going to be 9, which once again is just simply 3 times bigger for that z component. So you've just scaled it through. So in general, when we are having a k and we're trying to multiply it by a vector as it would have those particular components, then this is nothing else but just bringing the k inside of the vector. So k multiplied by vx, k multiplied by the vy value, and then k multiplied by the vz value. So that is really nice. It's basically just kind of like a distributive property that we would have. We can just distribute right across. And then, of course, we can visualize this in this particular way. Now, you can sketch it if you wanted to, but that's the component of the scalar multiplication. Now, the last one, so the last item with the dot product is probably, I guess, one of the harder ones to think about, and you would think, so I'm going to just copy this, that this would be in some way complicated. It turns out that it follows the same process as 2 dimensions. So just as a review, so if you recall, kind of dot product for 2 dimensions, what we would have is if you had, this was my first vector, so the x component, and then the y component, and it was dotted with, so the dot product, with the u vector, so the x component, and then the y component. So we knew that the dot product right here, so if you wanted to have this was just simply the actual magnitude of the v vector and then multiplied by the magnitude of the y vector and multiplied by the angle between them. So really it's just a projection of one vector on top of the other in 2 dimensions. Now, that's very easy to be able to see in 2 dimensions because let's say if this was my v, okay, and this was my u, or vice versa, it doesn't matter, okay, and then you can really imagine that here is your angle in between. So, if this is my v and this is my u, then you can take the magnitude, okay, of one, multiplied by the magnitude of the other, and then just take the cos, okay, in between, which is really, okay, would just simply be like a projection onwards, and it would just give you what the magnitude would have been there in between them. Now, for doing this, right, so if you were trying to do this throughout in the 3 dimensions, does this change in any way? Well, it doesn't, except once again, it's very difficult to try to visualize in 3 dimensions, or at least it's much harder to visualize depending on what the vectors are. So here we're in a plane, we're in 2D, but if you're only taking 2 vectors, you technically are in a plane. Now, the plane might not be the x and y, it might be some random plane, but you still do have an angle in between those 2 vectors. Now, it's much harder to be able to find that angle, but we can use the dot product to do that. Now, just to complete this 2-dimensional and kind of as a review, you certainly don't have to use this if you know that you have your vectors in your Cartesian format, because you can literally take these. And we have shown, and I've done actually the proof for this, that the actual dot product is nothing else but just the multiplication of the components, and then you're just simply adding them up. So this would have been the dot product in between these 2 particular vectors, and that would indeed be equal to this. Now, the proof for that, I've done it. I've put up a link up above there if you're interested. And we can actually extend that proof to 3 dimensions. It's going to take the same process. It's just going to have more components. But what it will show you is that if you do take 2 vectors, so now I'm going to write these out in 3 dimensions. So if you have, for example, Vx, this is Vy, and now we are adding a 3rd component, and now you're trying to dot it with another vector. So ux, let's say uy, and then uz, it still is equal to this right here. So that is the same. Now, finding the magnitude is not very difficult for a vector in 3D. So we can certainly do that, right? We can do these. Finding the angle is actually a little bit harder to be able to do. However, in 3 dimensions, we typically do utilize these in Cartesian vector form. So we have these in terms of their components. So finding the dot product is nothing extraordinary. It's going to be Vx multiplied by Ux plus Vy multiplied by Uy, which is the same as 2D, plus now your 3rd component, which is Vz multiplied by Uz. And there is your dot product. And again, you can prove this the same way as I did for 2 dimensions. Now, if somebody watches this video and maybe asks me, okay, can you prove that and make a video of it? I certainly can, okay? But I would challenge you, watch the 2D and try to replicate it with this, okay, in 3D, so that it really asks you and forces you to try to do those proofs on your own so that you'll understand it much better. But I'm happy to do it, okay, if I get a comment, okay, or an email at some point to try to do the proof for this. Now, if that's my dot product, what is really nice is because in 3 dimensions, now in 2 dimensions we ran into the same problem. So if you take this, so for example, I'm going to just kind of steal this, okay, along here. We know that this is, I'm going to paste this along right there. Let me maybe change the color. So we do know that the dot product between the 2 vectors is equal to that. And if you want to find the angle, then please don't forget, you can certainly isolate this, right? You can divide both sides, so you're going to get the dot product, especially when they're in their component form, right there, okay, as we have this value. So if we can find this dot product, we can now divide by the actual magnitudes between them, and we can find what this angle is exactly, right? So it's not a problem actually for us to be able to do that. Let me end the video actually with this. So let me take maybe, a couple of vectors that we've done. So I have been working with these vectors. So let's, try to take these. I'm going to copy it. I'm going to bring it down here. And this will be our example. Now, instead of adding, what we want to be able to do is we want to find the dot product in between these. And we're going to try to find the angle in between them. So now the dot product is going to give us this numerator right here. So if I do the dot product in between, what I'll find is, so 1 times the -3, which is -3, plus the 2 times the 4, which is going to be 8, plus the 1 times the -2, which is going to be -2, so it's going to be that. And if I now add them together, so this is going to be -3 plus 8, which is 5, and then 5 plus -2, which I guess is 3 right there. And that's my dot product. Now, those vectors, I don't have any units on them. You know, they probably will be dealing with units if you're working on applications, so maybe forces, maybe velocities, maybe something else. Now, in this case, if I have the dot product, okay, so which is my numerator right there, I can find the denominator here for each. So let me find the magnitude. So I'll find the magnitude of the first one. So the magnitude of the first one, so that's this one right here, is going to be the square root of 1 squared plus 2 squared plus 1 squared. And for that, so it's relatively simple. So 1 plus 4, 5, okay, plus 1, which is 6. So this is square root of 6. Now I can take the second one right there, and then the magnitude of that, that's going to be 9 plus 16. I'm already squaring it, by the way, plus 4. So that's going to be, I guess this is 20, that's 29. So the square root of 29. So what we have is, we can say cos theta is equal to the dot product, which was 3, divided by, now, the multiplication of the two magnitudes. Well, so let's try to find this. So I'm going to find my angle. So this is going to be cos inverse of, okay, all of this in here. I'm not going to rewrite it, but I can take out my calculator and pop it up. So here's the inverse. It's going to be 3 divided by, let me put the denominator in brackets. This is going to be square root of 6, and then that square root is multiplied by the square root of 29. So I can close this down and hit equals, and there you have it. So the angle in between those is, so 76.8, so let's say 77 degrees, okay, approximately. So you can find the angle between two vectors even in 3 dimensions if you wanted to. And that's pretty interesting to be able to do that. And the definition of this dot product holds true for 3D. It's interesting, it also holds true for higher dimensions, except it's very difficult to try to imagine what we are actually visualizing there. So that is what I wanted to pass on to you in this video, is basically extend the concepts from 2 dimensions to 3 dimensions. I have covered 2 dimensions in quite a few videos, and now I just wanted to extend the addition, subtraction, scalar multiplication, and dot product to 3 dimensions. All right, thank you for watching, and we'll see you in a future video. Bye, everybody.